After learning the concept of statistic, central limit theorem, now we will be moving on to our next part, which is estimation. So there are different kinds of ways that you can do your estimation. One of them is point estimation. Another one will be interval estimation. Okay. So this video's agenda is to start with point estimation. Okay. So what is a point estimation? A point estimate of a parameter theta is a single number that can be regarded as a sensible value for theta. Okay. Let's try to understand this with the help of an example. Okay. So let's say we have a population. There is a mean, right? And from this population, we are taking a random sample, say x1 up to xn. This is our random sample. Now, how can you estimate this population mean with the help of this random sample? We can do that by using sample mean. So this sample mean is an example of a point estimate. So we are denoting the population mean. We are trying to estimate the population mean with the help of a single number, which is our sample mean in this case. Okay. In general, a point estimate of a parameter theta, in this case, the parameter is the population mean, that can be regarded, sorry, of a parameter theta is a single number that can be regarded as a sensible value for theta. So our sample mean is a sensible estimate for population mean. Okay. A point estimate is obtained by selecting a suitable statistic. So in that case, we chose the statistic as sample mean and computing its value from the given sample data. The selected statistic is called the point estimator of theta. So this x bar is our, or the sample mean is our point estimator. Okay. In the next paragraph, we will see just what I told you. In the battery example just given, the point estimate of mu was 5.77. If the three observed lifetimes had instead been x1, x2, x3, use of the estimator x bar would have resulted in the estimate 5.40. The symbol theta is customarily used to denote both the estimator of theta and the point estimate resulting from a given sample. So basically, we are trying to say that if there is a parameter theta that we need to estimate, we can find out a suitable estimator and try to have our best guess. Okay. Okay. Let's see this example. An automobile manufacturer has developed a new type of bumper which is supposed to absorb impacts with less damage than previous bumpers. The manufacturer has used this bumper in a sequence of 25 controlled crashes against a wall, each at 10 miles per hour, using one of its compact car models. Let x equal to the number of crashes that result in no visible damage. The parameter to be estimated is p, the proportion of all such crashes that result in no damage. If x is observed to be small x equal to 15, the most reasonable estimator and estimate r. Okay. So we have n equal to 25. Why? Because the manufacturer has used this bumper in 25 controlled crashes, and x is our number of crashes in which there is no visible damage. Okay. And we need to find out the proportion of cases in which there are no damage. Okay. So the best way to find that out is to use x by n, this estimator, right? The estimator p hat equal to x by n. So this is the most reasonable estimator in this case to find out the proportion of crashes in which there is no damage, because x represents the cases where there is no damage and we are dividing that by n to get our proportion. Now the estimate will be small x by n, which is 15 by 25, because x is observed to be small x equal to 15. So our estimate value is coming to be 0.6. So this will be our point estimate in this case. Okay. So we need to know a couple of properties when we are talking about estimators, especially point estimators. One of them is unbiased estimator. So an estimator is said to be unbiased when the expected value of that estimator is equal to the parameter. So a point estimator theta hat is said to be an unbiased estimator of theta if expected value of theta hat is equal to theta for every possible value of theta, for all theta. Okay. So whatever be the value of the parameter that we are trying to estimate, the expected value of our estimator is equal to the value of the parameter. That is what we are trying to say when we are talking about unbiased estimator. But what if there is some bias present? Okay, so we will calculate that bias with the help of expected value of theta hat minus theta. So this formula will give us the magnitude of our bias. If theta hat is not unbiased, the difference is called the bias of theta hat. Okay. Now, when we were talking about that car crash example, we took p hat equal to x by n as our estimator. Now let's check whether this p hat is unbiased or not. Okay, so how are we going to do that? Let's take expected value of p hat equal to expected value of x by n. We know that n is a constant, so I'm taking that out. Expected value of x. Okay, now this x, what was our x? X was the number of crashes in which there was no visible damage. Okay, and this x is distributed as binomial in comma p. Why so? Because in each of the crash there is a certain probability which is small p, in which in small p of those cases there will be visible damage, and n is the total number of, basically total number of simulation that we are doing, right? So x is distributed like this, binomial n comma p. We know that what is the expected value of x? It will be n times p. So 1 by n times np, which is equal to p. So you can see that expected value of p hat is equal to p, right? So we can conclude from this that p hat, which is equal to x by n, this is a unbiased estimator of the population parameter. So see, the sample proportion x by n was used as an estimator of small p, where x, the number of sample successes, had a binomial distribution with parameters n and p. From here, you can find this out. Okay, now let's take a look at another example of an estimator, and let's check whether it is unbiased or not. Okay, so now let's see that this is our random sample x1 to xn, and all of these are independent and identically distributed. Independent and identical. Okay, and their distribution, all of these follow uniform 0 comma theta, and we want to estimate this theta. So this is our parameter. Okay, and we have a estimator theta hat as max of x1 x2 up to xn. Okay, and we want to check that whether this is unbiased or not. Okay, so this function max of x1 comma x2 up to xn will give us the maximum of these n values. Okay, now let's check how we are going to deal with this. First, we will find out the distribution function of this. Okay, so how we are going to do that? So probability max of x1 up to xn less than equal to small x. Okay, now if the maximum value between these n values is less than equal to x, then the second largest value will also be less than equal to x, right? Similarly, the third largest value will also be less than equal to x. So if the largest among these n values is less than equal to x, all of the values will be less than equal to x. So probability of, I can write it like this: x1 is less than equal to x, x2 is also less than equal to x, x3 is also less than equal to x, up to xn is also less than equal to x. And since I know that these are independent in nature, I can write it like this. So I'm multiplying all of the individual probabilities, and all of these x1, x2 up to xn, these are uniform distribute. These follow uniform distribution from 0 comma theta. So this probability will be x by theta times x by theta up to n times. So how am I getting that? Let's calculate the probability of the single one of them. So x1 less than equal to x. So 0 up to x. 1 by theta is the density function of the uniform distribution. See? And tx. So, sorry, this will be d. No, this is dx only, right? So from this, you will be able to get that x by theta. Okay. So now this is x by theta to the power n. Now we are going to find out. The density function. We found out the distribution function, which is x by theta to the power n. Now, how will I find this? I will differentiate this with respect to x. Okay. So d dx of this, right? So n x by theta n minus 1. So this is our density function. Okay. So if this is our density function, then we need to, okay, so one thing which I did wrong was, since this is ddx of x by theta to the power n, I will take this to the outer side, and I did one thing is wrong. So, yeah, this is the entire density function which you need for the next part. Now the expected value of expected value of theta hat will be integration of up to 0 to theta and in x to the power n this dx. Now in by theta to the power n x in plus 1 and plus 1 theta 0. I'm using the limits by n plus 1 and this will just be theta this, right? So n by n plus 1 times theta. So this is your expected value of theta hat. Now you can see that expected value of theta hat is equal to n by n plus 1 times theta, which is not equal to theta because n by n plus 1 is always less than equal to 1, right? So this theta hat, which we took as the max function of this x1 to xn, this is a biased estimator, not an unbiased one. Okay, so this will be biased in nature. Now let's again move back. So you can see the entire example which is given here. So I basically did this one only. The expected value of theta 1 hat, where theta 1 hat is nothing but the max function. Okay, so this is n by n plus 1 times theta, which is less than theta. So this is not unbiased in nature, and you can calculate the bias as well from here. So your bias will be expected value of theta hat minus theta, which is n times theta by n plus 1 minus theta, which is minus theta by n plus 1, right? Okay. Now, another property that is extremely important is estimators with minimum variance. So among all estimators of theta that are unbiased, choose the one that has minimum variance. The resulting theta hat is called the minimum variance unbiased estimator of theta. So if there are some pool of estimators, let's say theta 1 hat, theta 2 hat, theta 3 hat, all of these are unbiased in nature. Okay. So with all of these estimators, we are trying to estimate one single parameter value theta. All of these estimators are unbiased in nature. So which one of them will we choose? Okay, so we should choose that estimator which has the minimum variance of them all. Okay, so which we will check that out of these three, which one has the least variance, and we will pick that. Okay, see that the PDF or the density function is present here for theta 1 hat and theta 2 hat. You can see that for theta 1 hat, the variance is much less. It is an extremely peak function like this, and for the other one, it is all over the place. So it has much larger variance. So if I need to choose between theta 1 hat and theta 2 hat, I will choose theta 1 hat because it has lesser variance. Okay.